So let's talk about electron configuration basics. So because when you're completing orbital maps or electron configurations or noble gas configurations or orbital box notation or even Bohr models, they all follow the very same basics. So a lot of these basics apply to almost everything moving forward. So when we're talking about how orbitals fill, how we do orbital rings, how we do orbital maps, how we're talking about spins, how we do all of these things, we're talking about the basic electron configurations. And so they're all the same. So this is a very important set of slides because it's giving you the set of rules for how all electrons act for the remainder of chemistry, basically, and really for electron configurations. So one of the main things we talk about is ground states. And that's a ground state is the lowest energy state of a configuration. If you think about it, electrons, atoms, they're all really lazy. They don't want to spend a lot of energy trying to hold electrons in at higher orbitals. They want to hold their electrons at the lowest energy possible because they don't want to spend a lot of energy. So this lowest energy state of a configuration is called a ground state. Then we've been talking about row numbers. They're also, a lot of them are also called quantum numbers. And this is the relative size and energy of an atomic orbital. So for S and P orbitals, they're always the row numbers. D orbital, your quantum number is rho -1. It's 1 less than S and P. And for the F orbital, it's rho -2. It's 2 less than S and P. So if I'm going to do this, not that. So quantum numbers, S and P, those are your row numbers. They match perfectly. D, the quantum number for D is rho -1, and the quantum number for F is rho -2, and that's from where it jumps down in D. Okay, so let's talk about the Aufbau principle. Aufbau is a guy who made the really important determination and made a principle out of it that each electron occupies the lowest energy orbital possible. Meaning, you're not going to fill in row quantum number 4 before you're filling in quantum number 1. And the importance is it explains, one, how orbitals fill, and then why the D and F orbitals, they jump back, meaning how they can go back one. Because if you're looking at a, like an S orbital, I'm not very good at drawing these, but the S's are kind of like a big circle. The P's kind of look like a clover leaf. And again, this is on like a 3D scale. And if you were to kind of put one on top of another, pretend that I can draw. Not really. There's empty spaces, so they go back in and fill in these empty spaces because it's a lot easier to try to fill in those empty spaces. It's less energy than to hold them out at new energy levels. So then there was this guy named Pauli, and he determined the Pauli exclusion principle. And the Pauli exclusion states a maximum number of 2 electrons can occupy a single atomic orbital, but they must have different spins. So when we're talking about the S block that has 2 possible electrons in the S block, because it has 2 rows, it will be denoted by a single box. It has 1 box, and with an upspin and then a downspin. The P block that has a potential of 6 electrons is denoted by 3 blocks. So this is for your orbital box notation, and we'll go into this deeper when we're discussing orbital box notation. And each box has one spin up and one spin down. D block, which has 10 electrons potential, always is shown by 5 blocks, and F block that is shown as a 14 electron potential is shown by 7 blocks. They're all up and down. They do fill in specific spins first as defined by Hund's rule. And Hund says, single electrons with the same spin must occupy each equal energy orbital before additional electrons with opposite spins can occupy the orbital. That's a very fancy saying. You have to have all your up spins first before going back and filling in all your down spins. So if you have 3 electrons for the P block, you wouldn't have up, down, up. You'd have up, up, up. And the other thing that's very important is that you always show all the boxes for the blocks when you're discussing it. If you look over here, this is an S orbital. These are your P orbitals. They're going to fill in blue, blue, blue before they fill in yellow, 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 that type of things. So the importance of Hund's rule broken down into, just a quick overglance as it determines how electron spins will fill, especially when we're talking about like orbital box notation. So as we said before, you've got to show all the boxes. So S has 1 box, so it's going to fill up and down, just like S has 1 circle. P has 3 boxes, just like a normal P has 3 clover leaves, and it'll fill up, 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 then down, down, down. D is a more abstract type of thing. It has a funky shape, but it is represented by 5 boxes, so it's going to fill up, 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 then down, 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 down. And then the F is even more obscure shape. It's going to represent by 7 boxes, and it's going to have up, 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 up for 7 times, followed by down 7 times. And that's the importance of Hund's rule. It tells how the spins are going to be in all of the orbitals. Okay, so let's look at the periodic table. I've broken it down into the different blocks by color. So we were talking about the S block being able to have 2 electrons represented by 1 box. It has right here, you can see that it's outlined in green. So it's the alkali metals, alkaline earth metals, and then helium over here. The P block is this yellow over here, has a potential of 6 electrons, 3 boxes. And if you look at it, it covers 6 columns from the boron family all the way to the noble gas family. Helium is not part of the P block. It is still part of the S block because helium only has 2 electrons. The D block is here. It represents 10 columns, 10 potential electrons, 5 boxes. And if you're looking at it, it's transition metals. It's the entire block of the transition metals, which is 10 columns long. Then the F block are your inner transition metals down here, 14 columns, so 14 potential electrons, 7 boxes. So let's talk about the basics of orbitals. So we've talked about orbitals before, and that's how you have your S, P, D, and F blocks. Those blocks are also called your orbitals. So you have an S orbital, a P orbital, a D orbital, and an F orbital. And they have a lot of the same basics as the blocks with a little bit of a difference. So your S block has a maximum of 2 electrons. Your P block has a maximum of 6 electrons. Your D block has a maximum of 10 electrons. And your F block has a maximum of 14 electrons. But please note that your elements can have multiple orbitals depending on where they are. So for example, if you put your hand on magnesium, it's just in the S block. It's in the first row. But if you put your hand on fluorine, you got to fill in the S block first and then go over to the P block. So when we're talking about the orbitals, we're really talking about that last row of things that'll fill in order to get to that final electron. So bromine, if you put your hand on bromine and look at that final row, it's S, D, and P blocks. Zirconium is just the S and D block. Astatine is S, D, F, and P blocks because of how they fill and bounce around. So another way of looking at this is we're going to be talking about orbital maps, but by organizing via quantum number. So this is a basic orbital map. We're going to be discussing these when we talk about orbital maps tomorrow. So quantum number 1, you have 1s2. Quantum number 2, you have 2s2, 2p6. Quantum number 3, 3s2, 3p6, 3d10. 4, 4s2, 4p6, 4d10, 4f14. 5, 5s2, 5p6, 5d10, 5f14. 6, 6s2, 6p6, 6d10. 7, 7s2, 7p6. And we're going to go further into orbital maps when we discuss our orbital maps, but that is not today.